Hi, I am Mohammad Koosha, and this is a lecture on the paper with the title FAHP-OF, a new method for load balancing in RPL-based Internet of Things. So I'm gonna start this talk with a little bit background about 6LOW PAN stack of protocol, and then RPL routing protocol designed for 6LOW PAN, and then I'm gonna talk about the importance of optimized routing in RPL. Then I'm gonna talk about FAHP-OF, which is our uh, proposed method for optimized routing in RPL. Then we're gonna have the results and conclusion sections. So 6LOW PAN is a stack of protocols designed for enabling tiny smart electronic devices to connect to the internet. In the lower layers, it has borrowed a lot from the PANs or the personal area networks, as it is a very sophisticated protocol for dynamic wireless networks. In the upper layer, it has inherited mostly from the IP world. And also, as we can see here in the middle, there is an adaptation layer for removing the inconsistencies between these two stack of protocols. But what we are more interested in here is actually the RPL, the network layer protocol named RPL. So RPL stands for Routing Protocol for Low Power Lossy Networks, or LNNs. The basic idea is the wireless transmission of data packets hop by hop within a network of tiny small electronic devices that each may have multiple sensors and that they can produce different types of data. Multiple applications may be required to be rendered on IoT nodes, and each may have different QoS requirements. Consequently, RPL makes multiple instances of a network. In each instance, nodes make one or multiple loop-free structures named DODAG, and each DODAG has a root node that connects the DODAG to the internet. So we can see here in this picture that how RPL actually works. The whole light blue body here is an RPL instance. A node can be a member of one or multiple instances in a network based on the applications that are rendered in that node. Within this RPL instance, we can see two pink clouds that are actually two DODAGs that, as we said earlier, are loop-free tree-like structures. Each DODAG has a root node, which is shown here with the red color, that connects the DODAG to the internet. The important point is that within an instance, a node can be a member of at most one DODAG, and no more than that. As we can see, each node has a parent that receives its child's packet and transmit it towards the root node. But how nodes choose their parents? They receive some info from a couple of neighboring nodes and decide what node to pick as a parent using an objective function, or OF. And this means that an objective function determines the structure of a DODAG. The critical issue is that in IoT nodes, in IoT networks, the nodes are pretty tight on resources like energy, computation, or storage. So an optimized topology is extremely important for traffic load balancing, and also decent network performance metrics like packet delivery or packet drop or packet delay. And as we said in the previous slide, the DODAG, or equivalently network structure, depends on how the objective function actually chooses a parent for a node. But there are two major problems when coping with this issue. First, an objective function has to be a lightweight solution, so not to put more energy or consumption stress on nodes. Secondly, the solution has to consider a wide range of factors, uh, for example, node or metric factors for an optimized solution. Here we propose FAHP, which stands for Fuzzy Analytic Hierarchy Process Objective Function, as a lightweight multi-criteria objective function. FAHP-OF uses fuzzy logic as a soft criteria lightweight decision-making system to avoid hard boundary decision-making situations. Also, FAHP uses AHP method for comparing variables of different kind with different levels of importance. In this picture, we can see different phases of FAHP-OF. At first, a node receives info from a set of eligible parents. The info includes ETX and RSSI and hop count from the root node. In the fuzzifier layer, these values are translated to qualitative values like low, medium, and high. An inference engine here actually works based on AHP method that sorts the degree of eligibility of all nodes. And at the fuzzifier, we select the best parent for the node. AHP is a method for comparing the variables that are of different kinds and have different relative importance towards each other. Here we can see a table assigning numeric values to each level of importance. For example, equal importance is 1 and extreme importance is 9. Next, we can see a table named pairwise comparison metrics that determines the relative importance of input variables with respect to each other. At last, we calculate an importance weight vector for each input. And finally, we will calculate a rank for each of the each of those nodes from our set of eligible nodes to actually assign a rank to each of them. So at the simulation parts, we have used Koosha simulator for the simulation with the parameters below for networks of 10, 20, and 30 nodes. On the right, we can see a visualization of a scenario of 10 nodes. First, we have calculated end-to-end delay for these three networks, the networks of 10, 20, and 3 nodes, using our proposed method FAHP-OF and also RPL's original objective functions that are MRHOF and objective function 0. As we can see, our method has outperformed the other two objective functions for all three scenarios. Here, as we can see for the FAHP-OF for the scenario with 10 nodes, in all three groups, we can see that end-to-end delay is much less for FAHP-OF. And we also have compared our method in case of packet delivery ratio, which is the ratio of the packets received to the destination between two links, between two nodes at the two ends of a link. And here, as we can see, also FAHP-OF has outperformed the other two objective functions with almost more than 70% of 70% packet delivery ratio. So in this work, we introduced a novel FAHP, a novel objective function for parent selection in RPL routing protocol. FAHP-OF, we introduced FAHP-OF as a lightweight multi-criteria decision-making objective function that is based on fuzzy logic and AHP method. We have through our simulations, we evaluated end-to-end delay and packet delivery ratio for showing the superiority of FAHP-OF in comparison to RPL's original objective functions. In future work, we will investigate FAHP-OF with more diverse input variables, and also we will compare it with more diverse objective functions. Thanks for your attention.